Let's look at this 2020 AMC10A problem 7. The 25 integers from -10 to 14, inclusive, which means that including -10 and 14, can be arranged to form a 5 by 5 square in which the sum of the numbers in each row, the sum of the numbers in each column, and the sum of the numbers along each of the main diagonals are all the same. What is the value of this common sum? So this, of course, is something called a magic square, as we learned. In this 5 by 5 square, let's just draw it. 2, 3, 4, 5, 1, 2, 3, 4, 5. We're going to fill those 25 numbers from -10, -9, all the way to 9, 10, 11, 12, 13, 14. Those 25 numbers fill into this square such that the sum of each row, the sum of each column, and the sum of the two main diagonals, this diagonal and this diagonal, are all the same. What is the value of this common sum? Now, for this kind of question, let's assume the common sum is a number s. The common sum is s equals s. So that means each row is summed up to be s. This row is also s. This row is s. This row is s. This row is s. And this column is s, 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 s. Everything the same, and then the main diagonal as well. How are we going to find this s? What this s? At first appearance, it looks like the problem, it's very difficult to start. But remember, there's something invariant about this. Even though we don't know how those numbers are filled, we know the numbers. If you look at all the 25 numbers, these numbers is the set, or is just these 25 numbers from -10 to all the way to 14. So if I adding all those numbers together, even though I don't know the ordering, I know the whole sum. So the idea is, if I'm adding the sum of this column to 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 the sum of this column, so I'm thinking of adding the sum for the first column, the sum of the first column plus the sum of the second column plus the sum of the last column. So basically, I'm adding the sums of each column, the fifth column. This will be equal the sum of every number in this square. Agree with this? Think about this for a moment. This sum, the sum of the first column, is the sum of these 5 numbers. The sum of the second column is the sum of these 5 numbers. And the sum of the last column is the sum of these 5 numbers. So if I'm adding the sum of each column together, I'm adding every numbers in this square. Okay, correct? And the sum of first column, of course, we assume that it's a common sum, it's s. So one way, on the left side, I know this sum of all the 5 columns is just equals 5 times s, because each column is s, so 5 times s. But the sum of every number, even though we don't know the order of these numbers, is going to be just a sum of the 25 numbers that we start with, minus 10 to 14. So this equals minus 14 plus minus 9 plus all the way to, I'm going to put 9 and plus 10 plus 11 plus 12 plus 13 plus 14. Now this sum, just realize that from minus 10, minus 9, all the way to 9 and 10, this just cancel each other because they are, you can pair them together. Minus 10 and 10 is 0. Minus 9 is 9, 0. And so on and so forth. This is just equals 0. So this whole sum just equals 11 plus 12 plus 13 plus 14 equals 50. And again, you can just using the technique of pairing them together. This is 25, this is 25, so the whole thing equals 50. So that you know that 5s equals 50, s equals 10. And that is the value of this common sum. And here you realize that we only use the fact that every row has the same sum. We don't even need the condition that every row has the common sum as well, and not to mention that we don't use this, the sum of the two main diagonals also share the same sum. We're only using this fact. Each column has the same sum. This consideration of using the whole, adding all the numbers together without even considering their ordering is a very, very important technique.